This video is on the product and quotient rules, two strategies for finding derivatives of products and quotients. I'm going to begin with a review of motion, and if you don't need this review, you may just want to skip ahead to the product and quotient rule. In this warm-up, we have a graph, and some things that are important for us to identify is the fact that this is a velocity graph, because the kind of graph we have determines how we're going to interpret the questions. So we have the velocity graph of a projectile as it flies through the air, and you can see the window that this graph is based on. All of our questions that we're going to answer, we're actually, instead of starting at a time of -1, we're actually going to start all of our questions assuming that the particle starts at time 0. So just be aware of that when I answer the questions, that I am focusing or assuming that the time is starting at 0 and not at -1. All right, first question. On what interval is the object rising? Now remember, this is a velocity graph, and velocity indicates two quantities. Velocity indicates speed and direction. And what we're concerned about in this particular case is the direction of the particle. So we need to know the sign, or consider the sign, positive or negative, of the velocity. So if the object is rising, it's rising when velocity is positive, so that would be in this particular region right here. So the particle is rising from 0 to 1, 2, 3 seconds, and then it's rising again from, it looks like 1, 2, 3, 4, 5, 6, almost 7, like around 6.9, and it goes on, if the graph goes on forever, it goes on to infinity. Now the way we're going to write that, let me pull this down a little bit. So the object is rising. Since 0 is, we're considering it an endpoint, the object is rising from 0 to 3, and 3 is open, and then the object begins to rise again. We'll say it's about 6.9, could be 7, we're just making an estimate here, to infinity. So that's when the object is rising. Now the object is falling whenever the velocity graph is negative, so that would be in this region right here. So the object is falling from 3 to 6.9. Next question is, when is the object stationary? Now if an object is stationary, then the velocity is equal to 0. So we can see that the velocity is 0, at 3 seconds, and at 6.9 seconds. Letter C, when is the object moving fastest? Well, the object is, when we're talking about fastest, we're talking about speed. Remember that speed is the absolute value of velocity. So when I'm going to consider when the object is moving the fastest, one way that I can do this is to make this given graph into a speed graph by taking the negative region that we see down here, flipping it up and making it positive. And let's see if I can count this. I've kind of got my graph messed up here. 1, 2, 3, 4, 5, 6, 7. That looks like about 7 up, and 1, 2, 3, 4, 5 down, assuming that I'm counting accurately. 1, 2, 3, 4, 5. It almost looks like that the velocity here is a positive 5, and the velocity here at the minimum is a negative 5. So the fastest that the object travels occurs at a time of about 1.25, again approximating, and again at about 3, 4, maybe about 4.25. So again, remember that the fastest is when the velocity has its greatest absolute value. Now the slowest that the particle moves, sometimes students think negative velocity. That's not what we're going to think about. Remember, you cannot go slower than a velocity of 0. You're not moving. So when the particle is stationary, that's when it's slowest. These two are basically asking the same question. All right, let's move on to the second graph, which this time is a position function. So now we have to think a little bit differently than we were thinking before, or our interpretation of the graph has to be different. So since this is a position function, again, we're going to start at a time of 0. The first question is, when is the object rising? Well, since this is a position graph, the object is rising when the position graph is increasing. So we can see the position graph is increasing in this region. And that looks to be about, again, it's a little bit off 1. So we'll just say, for simplicity's sake, let's just call this 1. Let me erase that. That doesn't look very good. Come on. Okay, my Promethean board wants to freeze up on me here for a second. Okay, so we'll say that that's about 1.25, and that if this is 1, 2, 3, 4, that this maximum occurs at about 4.5. So the particle is rising from approximately 1.25 to about 4.5. And then on a position graph, when the graph goes down, the particle is falling. So down, 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 decreasing, 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 down, down, down. So the particle is falling from about 0 to 1.25, and then again from 4.5 to infinity. The particle is stationary when there's no velocity. Now remember, same idea, we want the velocity to be 0, but velocity is the derivative or the slope of position. So if you take a look at this graph, we're basically looking for horizontal tangents. We have one here, and we have another one here. So at 1 second and at 4.5 seconds, the object is stationary. Object is traveling fastest. Now this one can be a little bit tricky because, again, we're looking for the, if you will, the largest positive slope or the largest quote-unquote negative slope, or the absolute value. So this would be kind of approximating where the slope would be the steepest. Not going to hit that one too much on this particular question, but the slowest, again, is still the same question as when is the particle stationary, so when there's no velocity. And on the graph, sketch a possible graph of v of t. I'm going to save that for class time, and I'm going to go on to the product rule. This page is in your packet, and again, this is simply a strategy for finding derivative, as you can see. The product rule is used to find the derivative of a product of functions. We already have the constant rule. The derivative of a constant is 0. We have the power rule that allows us to take the derivative of power functions. So now in this particular case, you can see we're finding the derivative. There's my, that tells me to find the derivative of a product, a multiplication of two functions. When you find the derivative of a product, you simply use the product rule, which says take the first function multiplied by the derivative of the second function plus the second function multiplied by the derivative of the first function. And I've written that in words for you right here. So as you practice the product rule, you just want to keep saying that over and over again until it gets into your head, until you've memorized it. So, for example, in problem number 1, we have a product of two functions. This is the first function, 2x minus 3, and this is the second function. So to find the derivative of that, we take the first function times the derivative of the second. The derivative of x plus 5 is simply 1 plus the second function, which is x plus 5, times the derivative of the first, which is 2. And now all we have to do is clean up a little bit, so we get 2x minus 3 by the distributive property plus 2x plus 10 combine like terms and we get a derivative of 4x plus 7, which makes sense because we know if we multiply this out that the original function would be quadratic and its derivative is linear. Number 2, we have a product. Our first function in this case is x, and our second function in this case is sine x. So this is the multiplication of x times sine x. The derivative of this function would be the first function, x, times the derivative of the second. The derivative of sine is cosine, plus the second function, sine, times the derivative of the first function, which is just 1. And really pretty much all we can do. If we wanted to drop the parentheses, we could, but there's no terms that can be combined. This is the slope generator for this particular function. Not too hard. Problem number 3. This time we have 3 terms. So this is term number 1, term number 2, and term number 3. Remember, terms are separated by plus or minus signs. Now, the second term is what I'll basically call a normal term, something we already know how to take the derivative of without applying anything different. The third term is a power function, and we know how to find the derivative of that. But the first term is a product. And in this product, we have the first term, which is 2x, and we have the second term. Also, remember, it's a good idea to rewrite the third term as a power function. So we get 5x to the 3/4. All right, so here we go. I'm going to find the derivative of the first term, which is the 2x cosine x. So I have the first times the derivative of the second. The derivative of cosine is negative sine, plus the second term, or the second function, cosine x, times the derivative of the first function. Now, all of that right there was the derivative of the first term using the product rule. Now I'm going to go to the second term, which is 2 sine x. The derivative of sine is cosine. Notice again, I take the derivative of that term just normally, nothing fancy. And then the derivative of the third term, by the power rule, we're going to multiply 3/4 times 5, so that gives me 15/4 x. Decrease the power by 1. 3/4 minus 4/4 is negative 1/4. And remember, I said you can leave that now. The only cleaning that you can do here, maybe drop some parentheses. This could become negative 2x sine x plus 2 cosine x. Oops, and then we got a term that's going to cancel out here, don't we? Minus 15/4 x to the negative 1/4, and then these two terms will subtract out, and so we end up with negative 2 sine x cosine x minus 15/4 x to the negative 1/4. I'm not going to rewrite that. All right, let's go on to the quotient rule. Obviously, if the product rule is used to find the derivative of a product, then the quotient rule is used to find the derivative of a quotient. Now, there are lots of little chance rhymes, whatever you want to call them, to remember the quotient rule. I've written it out symbolically for you, and then I have a little way to remember it. Most students tend to like this. We're finding the derivative of a, this is what I'm going to call the up function, at least in terms of the way I'm asking you to remember it. And this is the down function, as you can see from the notes. So when you find the derivative of a quotient, it's the down function multiplied by the derivative of the up function minus the up function times the derivative of the down function over the down function squared. Now, the easiest way to remember it, and literally you just say it over and over and over again, down d up. The d stands for derivative, of course. Down d up minus up d down over down down. Maybe pause the video and say that 10 times. Down d up minus up d down over down down. Believe me, if you keep saying that, you'll remember it forever. All right, number 4, we're going to find the derivative of a quotient. So this is my up and this is my down. So the quotient rule, down d up. I have to take the derivative of the up function. So that's going to give me 4x minus 4. So that was down, d up, minus up. The up function is 2x squared minus 4x plus 3. D down, the derivative of the down function is negative 3. And that's over down, down. So we get 2 minus 3x quantity squared. And you don't need to square that out, but you do need to clean up the numerator. So let's see if I can clean that up a little bit. Basically, actually, in the interest of time, I'm not going to clean it up, but you're just going to distribute and combine like terms. If the numerator will factor and we can reduce anything, fine. If not, it's just going to be that term over the denominator squared. So again, distribute in the numerator, combine like terms, and that would be your answer. Number 5, this is my up function, and this is my down function. So by the quotient rule, let me change colors here. By the quotient rule, I would have down, which is 21 e to the x, d up, power rule for the first term, so 2/3 of 6 would be 4x, decrease the power by 1 to the negative 1/3, minus 2. Okay, so that was down, d up, minus up, 6x to the 2/3. Notice I don't do anything to that. That's the up function. D down, the derivative of 21 e to the x is 21 e to the x, over down down, which would be 21 e to the x squared. And you can leave it like that. That's perfectly fine. The only thing I'm now going to do, and I don't have space to show it here, but I'm going to distribute and distribute, distribute and distribute, or I could actually factor the 21 e to the x out and combine like terms. And we'll talk more about cleaning in class, but mainly I just wanted you to see how the quotient rule works. The cleaning, there are lots of questions that arise on that. How far should I clean? How much should I clean? And we'll take care of more of those questions in class. Let's see if I have anything else on the next page. It looks like not. The assignment is here, and there's a reminder that on my Edline page that I also have another derivative by product and quotient rule. Those are the Patrick videos, but now there's this video as well. So anyways, you should have lots of resources to be able to help you do this.